I'm the PhD student of the Faculty of Mechanical Engineering of Slovak University of Technology, and today I would like to present to you part of my PhD thesis about the possibility of the use of the digital image correlation for a measurement in notch specimens and especially in sharp specimens. So, as you probably know that the fatigue lifetime is, or fatigue life is significantly affected by notch effect, and sometimes arises a demand to measure, for example, a stress concentration in the notches, which is problematic with the strain gauges because of the complex shape of the specimen, or sharp strain peaks, which would be averaged through the length of the strain gauge, and therefore there comes to mind all of the optic methods, for example, photoelasticimetry, ESPI, or digital image correlation. You probably, most of you know about the digital image correlation, but I will give a brief introduction to that. So it always starts with some speckle pattern on the surface of the specimen. You have to acquire multiple images of the surface. First one is most of the time an unloaded reference, and then some loaded specimens. And by the evaluation, you have to create some grid that's very similar to the finite element mesh, and then through a numerical approach, find a displacement vector of each of the point between the reference and the loaded image, and then from the displacement field you can calculate the strain field. And here comes a little bit of a problem, because of the displacement data is most of the time affected by some noise. And when you calculate the numerical gradient to get the strain field, this noisy data, this noise in the data is most of the time, not most of the time, always magnified. Therefore, most of the DIC systems use some kind of a filter or smoothing algorithm or fitting algorithm. In our case, it's a spline polynomial and the smoothing is done by the curvature, by restriction for the curvature of that shape of the surface. And the problem in the notches becomes, because most of the time in the case of small notches, the results tend to be dependent on the parameters of that filter. So that's the thing. First of all, we start with some easy examples, and that's the open hole tensile test. We had two configurations. First one was a side view, and the second is so-called symmetric view. At the side view, that's quite useful, but the problem was that the hole has to be relatively large to get an appropriate result. We get the results around from 3 to 3.05. It's not exactly 3 because that width of the specimen is not infinitely wide, but it was a relatively good result. On the other hand, the symmetric view has some drawbacks, because you can measure only the cylindrical shape of the specimen, but it has several advantages. And the first and the most important is that you can measure with this configuration much larger specimens, or specimens with much smaller notches. Then we came to second geometry, and it's this one, with the notch right here and right here symmetrically. This has some other advantages, that you can manufacture more specimens with smaller and smaller radii of the notch, and you can try the horizontal configuration of the cameras and the vertical configuration of the cameras as well, and compare them one another. Here comes the thing that we consider a notch as some kind of a smooth surface which has some minimum radius or some maximum curvature at the root of that notch. We don't consider something extremely sharp or infinitely sharp as like a crack. It has to have some kind of a radius in the root of that notch. And therefore, we came up with something like a number of pixels on the image acquired by the digital correlation system that is needed to get a good measurement result. That number of pixels tells us how large is the notch on the picture, and that is a measure of the amount of information on that picture acquired on that picture, and that radius tells us something about the sharpness of the strain peak. So we had multiple sizes of the, as I mentioned, we had multiple sizes of the specimens. As you can see, here are the horizontal and the vertical configurations, and here are the hysteresis loops for each measurement. Those dashed lines that stands out as just for an information, and every chart includes 3 lines. Every line is a different settings of the filter. And as you can see, if you have a relatively large notch, as this one, here is a little bit zoomed, that those 3 lines are almost the same. But if you go to the smaller and smaller notches, you can see the deterioration of the hysteresis loops and the slight difference of that curves. Here's the extreme result. The worse we get, that it really don't look like a hysteresis loop, and in the vertical configuration is the same. The effect of sensitivity on the notch parameter, on the filter parameters, and the deterioration of the shape of this hysteresis loop are good correlated, and these 2 effects are correlated with the sensitivity on the evaluation parameters like grid size or the subset size. So if you have a large notch, large on the image, it's independent or almost independent on those parameters. If you have a smaller one, every parameter gives you a little bit different result, which is not really useful. Therefore, we came with some kind of a sensitivity analysis. Here on the x-axis we can see the number of pixel per radius for each set of data, and on the y-axis there's a strain difference in some extreme settings of the filter. So this number, it's only a relative number, because if I would do a new set of measurements with, for example, a different spectral pattern, that line would be a little bit higher or a little bit lower, but we consider that the shape would be probably the same. But these values tells us how much can be the result affected with the filter for different sizes on the picture. This one chart is the same, just recalculated in a linear elastic region to the stresses for steel as a material. With these data and all the measured data, we considered that all the notches that were larger than 200 pixel per radius were relatively well measurable, or for us relatively well measurable. And the thing is that if we have in real life larger or smaller notch, it doesn't really matter, because we can change the measurement equipment. For example, we can change the camera for cameras with larger resolution, or we can change the optical system lens. We can use a microscopic lens, so the measurement equipment could be utilized to any practically any size of the notch. With this data, we came to the real measurements, for example, of this brake component. It was measured in this small notch right here. This is the one of the results. It was measured for two different measurement configurations. We've done multiple measurements with different angles and different distances from the specimen. It satisfies that condition that I mentioned in a previous slide, and it gives us a very good result. We compare the result with the final element model, and the difference was only 2 or 3%. So we consider it a good measurement. A next measurement was a measurement of a welded specimen. The main difference is that the geometry of the welded specimen is not accurately defined. It's something we can say that is random. This is a specimen cut out from the gas pipeline from, I think, C52 material. XX52. And we measured it in 3 positions or 3 cases. This is the first case, second one, and the third one. Here you can see the measurement from the first measurement case. Here you can see a little bit of an undercut, and that's these higher values is the undercut, and here comes the weld, and these are that's the smaller values right here, and this is the base material, or the generally affected zone, in better words. So here we have 2 significantly critical points. Initially, we considered this one as a more critical. Here on the scan of the surface, you can see exactly that right radius, and it's a bit larger radius. So it satisfies that condition quite well, and it gives a relatively good result. It's independent on quite all the parameters, so it gives a good result. Here we have some of the values. So we get some principal strains. We calculate the principal stresses for both of the points and get the stress concentration factors. These stress concentration factors are calculated from the component of the stress in the direction of the loading. And now I've talked only about the good measurements, but there are some worse measurements as well. For example, this one, that's the second case, and it's, I think, in this position, there's a bit of a problem, because here, I don't know if it's good visible, but here is a really extremely sharp notch, and if you measure it from a larger distance, you get a field like this, and when you're closer, you get a field like this, and it's going to be always dependent on the filter. So for this one configuration, we would need to have a different measurement configuration, different camera or the lenses to get closer to measure this one right here. And the third one, it's on the other side of the weld. It's like, let's say inside the pipe. It's also extremely sharp. This result is not so dependent on those parameters, but I don't really believe that result. So I don't want to mention those values. So let me summarize what I've been talking about. We consider digital image correlation as a quite well suitable method for a measurement in notch specimens and sharp notch specimens as well. But the notch has to be sufficiently large on that picture. Possible solutions for the smaller notches are, for example, a microscopic lenses or some kind of a change of a measurement equipment, or the thing I'm working on currently, and that's the filtering in the time domain as well. For example, if you have a time recording of some time recording or recording over time of some problem in the notch, you can filter those displacement data first in the time domain, then in the spatial, and then recalculate those strains and then stresses. So thank you for your attention.
Questions? Just before the sunset, please.
So if you have a certain geometry and you don't know exactly what the stress concentration will be,
Yes.
how are you going to determine which lenses you will use? How much you have to zoom in? So
That's a little bit of a problem to define. When we come to the certain, for example, welded structure, we have to look at it and try something, and that if it's going to be a wrong measurement, then change the lenses. But for example, for this measurement,
but usually you don't know which.
You usually cannot really, you usually cannot exactly define that this random notch is going to be, for example, with a radius of 0.5 millimeter. You can say it only plus minus. No. So it's a little bit difficult, but it can be relatively good determined.
Last question. Not
Thanks. But it's waiting the sunset.
yeah, I need something. Okay. Thank you very much.